You have sound? No sound? Sound on? Now it's on? Okay. Okay, everyone. So, I think we're good. So this is an announcement concerning the quiz. I already posted this info on CourseLink. Okay, regarding especially the location. So it's this Saturday at 10 a.m. The scope is until the end of nodal analysis, which is included in the quiz. And the location is in this building, room 2520. I said that before, I'm going to say it again. If somebody misses quiz 1 for whatever reason, then the weight of that quiz, those 5 points, 5% of the final, is automatically going to be transferred to the midterm. Okay, so I'm repeating that so it will be clear. I'm not going to repeat the quiz. Like this. Okay. Okay. So we finished chapter 3, and I'm going to start chapter 4 now. Chapter 4 is entitled Circuit Theorems. Okay, so in chapter 3 we had 2 methods. It was called like methods of analysis. For some reason they're calling these theorems. It's actually interchangeable. In some other books they lump everything under theorems, including the node voltage method and the mesh current method. But in our textbook, we have a new chapter. So we're going to see these 4 theorems. The first one called superposition. Second one, source transformation. Then we're going to learn about Thevenin's theorem and Norton's theorem. Now there's more stuff in chapter 4. I'm not going to cover the rest. Okay? Yes. This is not shared. Oh, how come? Why is that? Well, first of all, also I want to make you okay. Should. Thank you. Okay, so there you go. 4 theorems. I'm going to start today with superposition, and I'm hoping to fit and source transformation. I hope we have the time to do that. So we start with what we call the linearity property. So we say a resistor is a linear element, and we've seen that when we looked at resistors. A resistor has a linear relationship between the voltage and the current. So V equals IR, this is Ohm's law, okay? And if you draw that on a curve, the voltage versus the current, this relationship is going to give you a straight line passing through the origin. And that's why we say it's a linear element. Now we have this property called the homogeneity property. Okay. It says if V equals IR, then instead of applying V as V, or another way, if instead of I say K times I, so the voltage is going to be K times V. So in other words, if you multiply both sides of your relationship here, V equals IR by K, you get KV equals KIR. And what that means is if the input is multiplied by a constant, then the output is multiplied by the same constant. Now, it's not very clear when you're talking about a resistor, what is input and what is output here. But basically what it means, if the current flowing through it is I, R is obviously a constant. If a current flowing through it is I, produces a voltage V equals IR. If instead of I, you have a current K times I, therefore the voltage that you're going to obtain across your resistor is going to be K times V. Okay, it's pretty straightforward, and this is what we call the homogeneity principle. And then there is something else that also derives from the linearity. It's called the additive property. Now, what does additive property mean? It's here. Additive property means if you have like two currents, voltage V1, and then you have a current I2, when it passes through R, it produces a voltage V2. Now, the additive property says if you have that going through R, like I1 plus I2, it's going to give you a voltage equal to V1 plus V2. It's a simple math, and this derives from the linearity as well. Now, if I had an element where V and I are not represented by a linear property, let's say you have an element, let me try something, okay? I'm going to, do an element like that. This is V, this is I, and the relation square or alpha I square, like you have a parameter here. If you have something like that, it's non-linear. And you're going to find that those two properties will not apply if you had an element like that. You will not be able to have the homogeneity property because if current I becomes Ki, the voltage is not going to be Kv, okay? Because K is going to be squared here. And also, if you have I1 producing a voltage and I2 producing another voltage, if you have I1 plus I2 here, if you have I1 plus I2 squared in here, okay, it's going to mess up your addition. It's not going to be linear. So you can have elements that are non-linear. We don't have anything like that right now in this particular course. But this is important for the future because transistors and diodes, which are electronic components, are non-linear. They have a voltage current relationship, which is not, we're going to be using that. The other is that the response to a sum of inputs is the sum of the responses to each input applied separately. Okay? Okay. Linearly related to its input. Linearly directly proportional. General, and these In general, a circuit is linear if it's both additive and homogeneous. A linear circuit consists of only elements. So you're not going to ask yourself every time, oh, is my circuit linear? If you find that all the elements are linear elements, then your circuit is going to be linear. And linear elements are resistors, inductors, and capacitors, dependent and independent sources. Okay? And you shouldn't have diodes or transistors in a circuit because these are nonlinear elements. So we're safe. Everything we're going to see in this course is going to be linear circuits. Okay, let's see how we can apply the linearity principle here. For the circuit shown, find I naught. See, I naught is in this right side branch when Vs equals 12 volts and Vs equals 24 volts. Okay, now this circuit has only one independent source. This is considered the one input, which is Vs. The second source, which is equal to 3Vx, that's a dependent source. So it's in the mathematical sense. So we're going to solve this problem, and I'm going to use Vs equals 12 volts to solve it. Now, the trick here is just to show that if you know how much the current I naught is, if Vs is 12 volts, if I change Vs and I make it 24 volts, what would I naught be? You just double, exactly. Okay, so you don't have to solve the same problem twice. And that's the trick here. If you understand the linearity principle, you understand that if you solve it for Vs equals 12 volts, therefore I naught is going to double when Vs doubles. But that's a circuit with just Vs being the only or the primary input here. So let's solve it for Vs equals 12 volts. Minus and plus 3Vx, and Vx is here. We want to find I naught. This one. Okay, so when you have a problem like that, you can solve it whichever, I mean, there are many different ways to solve a problem like that. They're already giving us a hint because they're saying, okay, look at that, small I1, small I2. So it seems that using a mesh current method is advisable here. Okay, so that's also going to be kind of like a revision to do that. Like I'm going to start from here. I'm going to go in this direction. So I want to write a KVL for loop 1. So if you're going from here to there, your current is flowing like that. There's a drop of 6I1. Then as I'm going here, which is Vx, I'm gonna ground the loop like that. So I'm having, oh, how much is this? This is 4 ohm. As I'm going from here to there, I'm having another drop of 4. And there are no rises here. So that would be the first equation. But again, this Vx has to be replaced by something, because remember, your KVL equations have to always be in terms of your unknowns. And in this case, my unknowns are small I1 and small I2. So I have to do something with this Vx. Vx equals 2I1. I'm going to rearrange that. I have 6I1 plus I1 for I equals 0, right? 12I1 minus 4I2 plus 12 equals 0. That's my first equation. I'm going to write a KVL around loop 2. Starting again from the bottom here, if I go in this direction, I get a voltage rise of 12 volts. And then from here to there, I have 4I2 minus I1 drop. And then in this direction, a further drop of 4I. Okay. And we already have decided that Vx is equal to I1. So my equation now is going to be six I1 plus 12 equals 4 plus 8 plus 4 I2 minus 4 I1. So I'm gonna have this equation 6 I1 minus, so I have here 10 I1 minus 16 I2 plus 12 equals 0. That's equation 2. I could simplify these. So this one, in fact, becomes 3I1 minus I2 plus 3 equals 0. And this one here, let's take it there. Plus 6 equals 0. So these are my two equations now. So what I could do, from the first one, I could say that I2 equals 3I1 plus 3, right? And I'm going to use that here. So I have 5I1 minus 8, 3I1 plus 3 plus 6 equals 0. 5I1 minus 24I1 minus 24 plus 6 equals 0. So minus 19I1 equal 18. So I1 equals negative 18 over 19 amps. Now again, please revise with me, because sometimes some little mistakes are made here or there. Especially I don't like when I find numbers like that, 18 over 19. So just keep an eye with me if there's any mistakes somewhere. Sorry. Does anybody have a copy of the textbook with you? I saw some of you. Yes, you have the textbook? Yeah. Maybe you could just take a look and show me an example 4.1. What did they find for I1, just to make sure? Thank you. They're not even producing the value for I1. 6I2. But something doesn't look right. 12. Well, let's continue because they're solving it in a little bit of a different way. If this is I1, I2 equals 3I1 plus 3. Three times, yeah. Okay. So in the book, they're doing it in terms of VS, and then they are substituting for VS, and they end up getting us a value of I naught equals 12 over 76, which is the same thing, right? Okay. So we have a value for I naught when VS equals 12 volts. The second part is, we did all this effort. We wrote KVLs, we solved it, we solved some simultaneous equations, we have fractions, so you put in a lot of work here. You don't want to do the work again. So the whole point is, if VS equals 24 volts, I naught is going to be equal to 2 times 3 over 19, 6 over 19 amps. Okay? And you're done. So that's the main idea here for the linearity principle. Any questions? Could I move the paper up a bit? Yeah, sorry. Okay. Okay, so that's the first use of the linearity principle. We're going to see another example, example 4.2. Now, this is a very smart way to solve a problem. You have this big circuit where you have all those resistors. Five ohm, 3 ohm, 4, 2, 7, 6 ohm, and I have a current of 15 amps. We want to solve this circuit to find the value of this current I naught here. Now, they're doing it in a very, very interesting, very smart way. And you have to have, like what we talked before, like especially Ohm's law, you have to have that in mind. You have to see it clearly. What we could do, I could do 5 plus 3, that's 8 ohm resistor here. You see that? And then I do that in parallel with my 4 ohm. I'm going to get a new resistance. So all of that is going to be one new value of resistance in series with 2. Then I can take all of that. It's going to be one resistance in parallel with 7. And I can take all of that, one resistance in series with 6. And I'm getting all of this reduced to one resistor. That's the normal thinking. This was what somebody would do. And you would do 15 divided by this resistance would give you the value of the current flowing in this part. And then if you know that, you're going to kind of try to keep going backwards, dividing this current using the current divider rule, which is a perfectly valid way of solving this circuit. And in fact, I'm just even thinking now maybe we should do it this way. Just, let's do it like that, because that's also good training. So what do I have here? I have here 8 ohm. And then I have here 4 parallel with 8 equals 4 times 8 over 4 plus 8. Okay. And then it's going to be in series with 2. So you have 2 plus 8 thirds, 14 thirds ohm. That's all of that together. In parallel with 7. So you have 7 parallel with 14 thirds. That's 7 times 14 over 3 divided by 7 plus 14 over 3. That's 7 times 14 over 21 plus 14. So if I'm going to divide by 7, I get here 2 and I get here 3. That's 14 over 5. Okay? Just 2.8 ohm. And finally, the whole big thingy becomes one big circuit. Maybe it would be good to redraw these circuits. So I have and then I have here 14 third, right? That's one circuit that we had. Okay, and then we reduce that to six plus 2.8. Okay. 2.8. 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 Now these two together, that's 8.8 ohm. And it would give you current here of, I'm going to call that IS. (15/8.8). Okay, not a very nice number either. But if we say 14/5, yeah, maybe we can do that. 14/5 plus 6. So IS is equal to 15 divided by 44/5. So that would be the current IS. Now, the reason I'm showing you this is because if you have a current here, and then you try to go backwards, it's the same current IS here, it's the same current IS there. What does that mean? It means the current that we found is 75/44 is the current that is flowing through from the 15 amps into the 6 ohm into this one as well. But if you're trying to relate it to anywhere else in the original circuit, you have to be very careful. The common parts remain the same. So for example, if you compare this one to that one, this part here is common, right? This and that, they are common here. So the current I found here is the same current I found there. It is not the current in the 7 or in the 14/3. Now what do I need to do? If I have this current IS, then I can do a current division. And then I can say, oh, I can find a current here and a current there. So let's find the second one. This current here, I'm going to call it I2, for example. Okay. Now the current I2 would be IS times 7/7 plus 14/3, right? Current division. And so you would be going backwards, finding the current I2. If you have the current I2, the purpose why I'm doing this is to show you how, if you want to keep going backwards, if you find the value for the current I2 here, where is the current I2 in the original circuit? Now this is IS. This current would be this one, which you did not calculate. And I2 would be the current flowing here. Okay? And then from that, you would want to find the current I0 by again doing another current division, because if you have I2, it divides between this one and this one, and therefore you can find I0 using current division. So it is tedious, it's long, you can make errors, you have to do all those combinations of parallel and series resistors and stuff. So let's go back to the way it was solved in the book, because I believe it's a very smart way. I'm going to redraw that circuit first. Okay. Here's our circuit. We don't know what the current here is, I0. We want to find it. So we want to make an assumption. Okay. Now, is this correct? We have no idea. Is I naught 1 amp? We have no way of knowing. But we're making this assumption. We're going to see how we're going to use the linearity principle to use this assumption to solve the problem in an easier way. If this is 1 amp, the 1 amp is flowing like that, right? So how much voltage do I have across my 8 ohm resistor? So between here and here, I have the voltage here. I'm going to call that V1. V1 is 1 times 8 equals 8 volts. Okay? See, I'm using my 1 amp current assumption here to find the drop across of these two together, 5 plus 3, which is 8. So I found this V1, which is 8 volts. Now, if I know that this is 8 volts, how much is this current? See, we got 8 volts across from this node to that node. It's the same voltage across this resistor. So this current would be, Ohm's law would tell us that this current is 2 amps, exactly. Okay? Okay, let's go further. I have 2 amps flowing like this and 1 amp flowing there. Can I find how much current I have in this 2 ohm branch? How much would that be? 3, exactly, because of KCL. If you write KCL here, this current has to be the sum of these two. So I have here 3 amps. Excellent. If this is 3 amps, what is the voltage from here to here? I'm going to call that V2. 6 volts. V2 equals 2 times 3 equals 6 volts. Okay, look at that now. Look at this node here, and look at, the bottom node. That's all that is, just one node, right? Look what I'm going to do now. This node here is higher than the bottom one. The bottom one, we can say it's like ground, right? It's our reference. So this one is higher than that one by 4. This voltage is higher than this one by 6. Sorry, this one is higher than that one by 8. That's 8 V1. This is higher than that by 8. This one is higher than this one by 6. So how much is this one higher than that one? No, it's not 12. This is higher than that by 6. This is higher than that by 8. So how much is this higher than that? Okay, you have 3 nodes. Okay, one node there that's at 0. One node here that's at 8 volts. Another node here that's at 6 volts. Okay, how much is this one compared to the bottom one? It's 14 volts. Okay, that's 14 volts. So from here to there, that's 14 volts. Let's call that V3. In fact, if you want to just kind of, make sure that you're doing it right, let's do a KVL around this loop. If I start from here, I go from here to there, you get a rise of V3. Okay, that's before I know it's 14. If you go like that, from here to there, you have a rise of V3. And then from here to here, you have a drop of V2. And from here to here, you have another drop of V1. Okay, so V3 equals V2 plus V1. Okay, we found that this voltage is 14. How much is this current? Ohm's law again. 2 amps. And now we need to find this one. This current here has to be equal to the sum of this plus that, right? So this one is 2 plus 3, that's 5 amps. One final voltage, I'm going to call that V4. V4 equals, according to Ohm's law, 5 times 6. Now, like we found V3 by adding these two, I want to find the voltage here. I'm going to call that Vs. So V conventional, like typically you're trying to find somewhere, that's not the first method that comes to mind. But this is just to illustrate, like, some of the nice things that you can do if you understand the linearity principle. Yes?
Why to add V2 and V1 and not just V2?
It's a KVL situation. The question is to find V3, which is this one. Why did you add V2 over V1, not just V2? Well, V3 is the voltage difference between this node and this node. Okay? All right, so you have to find it from somewhere else, another path. How come you're saying V3, the difference between here and there is the same as the difference between here and here? This and that are two separate nodes.
Do we not assume that the lower node, like the green node in the circuit, is 0?
This one? Okay, let's assume this is 0. Okay, that's fine. If this is 0, what is the node voltage here? It's 8 volts, exactly. And this is higher than that by 6. So what is the node voltage here? 14. Okay, makes sense? All right. Any other questions? Okay. Now, something else that we're going to get from the linearity principle is what we call the superposition principle. I'm going to back a little bit. I'm going to go to the previous slide, this one. The additive property. The additive property is what we're going to be using for superposition. What does it say? It says that the response to a sum of inputs is the sum of the responses to each input applied separately. Okay, so we saw this one. I'm going to go forward again to the superposition principle. It states that The voltage across or current through an element in the linear circuit is the algebraic sum of the voltages across or currents through that element due to each independent source acting alone. I'll give you time to copy it and then I'm going to explain what it means. The voltage across an element is the algebraic sources. If you have a circuit which has two sources and you're trying to find which has two sources, and I could apply a node voltage method, write my KCLs and solve them simultaneously. We did that, okay? Or I could apply the mesh current method, because these methods are generic, right? They don't depend on having a particular number of sources. So if I have two sources, I can do that. What the superposition principle is telling me is if you have a circuit with two sources, you can say, okay, let's turn one source off. You make it equal to 0. Source in the circuit, that you're looking for. And then repeat the solution by keeping that second source, the one we turned it back on, and turning off the other one. Okay, so you keep only one at a time. And you solve the circuit again, and you get the new current through that element. Now, the principle says that the current through that element is the algebraic sum. It's the sum of the two currents you found each time by using independent sources acting alone. So steps to applying the superposition principle. Number one, you turn off all independent sources except one source. Now we say all except one because you may have more than two, right? You can have a circuit which has, I don't know, 4 sources. Okay, so you keep one and you turn 3 off. That's the idea. Number 2, find the output wanted due to that source acting alone. If you're looking for a current or a voltage, you try to find that. Repeat for each of the other independent sources in the circuit. So you're going to do this a second time, a third time, a fourth time, depending on how many sources you have. And at the end, the output that you're looking for, the voltage or the current in the circuit that you are actually looking for, you're going to get that by adding or finding the sum of the individual responses. But you take the sign into consideration. That's why it says the algebraic sum. Okay, so if a voltage is positive, the other is negative, you have to take that negative sign into account. Now the question is, how do we turn off a source? Because we say you turn off, sources repeatedly. Turning off a source means reducing it to 0. So if you're in a lab and you have like several sources acting on a circuit, if you have a voltage source, what you do, you turn it down to 0. So a voltage source is reduced to 0. 0 volts means it's a short circuit. Because if you say I have a source here and the source is now 0 volts, it doesn't mean it got disconnected. It means that, in fact, it maintains 0 volts across its terminals. That's what a voltage source does. But now it's a voltage short circuit because the two nodes across which that source is connected, now they don't have any voltage across them. They are at the same voltage, at the same energy level. So it's like you shorted them together. So this is how you turn off a voltage source. you put a short circuit in its place. If it's a current source, how do you turn off a current source? Again, you reduce its value to 0. So if you have a current source which has 0 amps, it means there's no current at all flowing through that element or through that branch, right? So this is equivalent to an open circuit. So turning sources off for the purpose of doing superposition, you turn voltage sources by replacing them by short circuit. You turn current sources off by replacing them by an open circuit. And there's an important note here. The dependent sources are left. You cannot remove dependent sources when doing superposition. You have to leave them. Okay. So let's do a problem here. It says find superposition theorem. Use superposition theorem to find V in the circuit. And the voltage here is V. Yeah, that's V. Okay. Superposition. What do we do? 1. Assume 6-volt source acting alone. That's the first step. I'm going to keep the 6-volt source and I'm going to reduce all other sources. I only have one. This is 3 amp. I'm going to reduce it to 0. So when I reduce the 3 amp to 0, remember, how do I do that? What does this source become? Short circuit or an open circuit? It's an open circuit, exactly, because this now becomes 0 amps. So 0 amps means no current. It's an open circuit. And the circuit now looks like this. I'm going to call this V1. And I have an open circuit. Now, this is a significantly simpler, nice little circuit to solve. What is V1? I'm going to use the voltage divider rule, right? I have 6 volts across 2 series resistors. I want the voltage across one of them. So V1 is equal to 6 times 4 over 8 plus 4. So this one actually this is 8 parallel with 4. How much is that? That's 8 over 3. Oh, okay. How much is V2? You have a current of 3 amps flowing through a resistor of 8 over 3. You can find V2 using Ohm's law. V2 equals IR, which is 3 times 8 over 3. That's 8 volts. Okay. So I found the value of that voltage that we're looking for due to the 6-volt source acting alone and due to the 3-amp source acting alone. Superposition principle says that's the last step. Using superposition, V that we're looking for is equal to V1 plus V2. That's 10 volts. Okay? Any questions? Does that make sense? Now, you could try to solve this circuit using any of the other methods that we've learned before. You can do a node voltage, a mesh current, whatever you want, and you can show that the voltage here effectively is going to be equal to 10 volts. So superposition is just another tool that you can use. Superposition is fun when you have a circuit like that. You know, if you remove some sources, you keep one source, it becomes a very simple circuit like this or like that. It's fun. You can do it very easily. Superposition sometimes is not a lot of fun when you have dependent sources because you cannot remove them. But the point with superposition is it's the basis on which you can build computer programs, software programs that do circuit analysis. Because if you have a big circuit and you have like 150 sources, you know, you have to have a computer to do that. And computers, typically, they use formulations where they have to use lots of equations that are solved simultaneously. And the way to build those computer software programs is by applying the superposition principle, by looking at the circuits, by keeping one source, removing the others, and then like doing all kinds of modeling like that. So this is another problem. Okay, find I naught using superposition. Now this is going to be a little bit more work because we have a dependent source that we cannot remove. So let's see what we're going to do. One, keep the 4-amp source, which means I'm going to remove the 20-volt source. The 5 I naught is there to stay. You cannot touch this one. So the 20-volt is going to be a short circuit, right? You get a short circuit here. Oh, and a resistor there, 4 ohm. Okay, so this would be the first circuit, and you need to solve that to find this current. I'm going to call that, say, I naught prime. Okay. Now, what method would you use to solve this circuit? Do you want to use a mesh analysis? You can have 3 meshes, like mesh here, mesh there, and a mesh there. Okay, that's okay. But you have a current source, so you're going to have to remember you had those exception cases. So I1 is already solved because it's going to be equal to 4 amps. That's a good thing. So, and you're left with 2 mesh currents. You have to solve that to find the value of I naught. Okay. If you wanted to do it using a node voltage method, what would you do? You would use this one to be your ground node reference. That would be one node with a current source that works well. That would be a second node. That would be a third node. And that would be a fourth node. Not very nice. Okay. And then you have this voltage source here. So you're going to have to kind of, take that as a super node. Well, sorry. Yeah. So these two, okay, we're going to assume it's like really one node. So that reduces the circuit a little bit. I'm going to say the sum of the currents flowing into that super node is equal to the sum of the currents flowing out of that super node. But again, I mean, this is one here, this one there. So you have 3 unknowns. So it's easier to do it using a mesh current method than a node voltage method. Okay. Just for the sake of time, I'm not going to do it in all the details. You can find it solved in the book. In fact, they are actually doing a mesh analysis for that, and they're finding the first current 52/17, I naught dash. Okay, so they're saying I1, I2, I3, I1 equals 4 amps. That's solved. That's nice to know. And then you solve, get I3, and then I naught is equal to I1 minus I3, which is equal to 4 minus I3, right? So you have to find I3. When you do that, you end up finding the value. That's sorry, all of that is I naught dash, right? I naught dash, according to the book, is going to be 52/17 amps. Okay, and then 2, keep the 20-volt source. So the 4 amps is going to become an open circuit now, okay? And you have okay, and now I want to find this current. I'm going to call it I naught double prime. So again, what method would you use? Okay, I could choose this one to be my reference if I'm doing nodal analysis. Okay, you can do that. And then this node is already solved because this is higher than that by 20 volts. So if you choose this one to be your reference, this one is 20. That's nice to know. It's done. But then you still have one node here, one node here, one node here, and one node there. Too many. You don't want to do that. And if you're trying to do a mesh analysis, you only have 2 meshes, so it's easier. You can do that. So you can do your mesh analysis. You don't have any current sources, no super meshes. You're just going to write your KVL across these 2. You're going to solve that, and you're going to get I2, because that's the one you need for I naught. And then I naught double dash is equal to negative I2. Okay? I don't know if I2 is positive or negative. Could be anything, and then you get your I naught double dash from there. So again, as I'm looking at the solution in the textbook, I naught double dash is minus 60 over 17. Okay? So that's the second phase of the solution. Finally, using superposition, I naught equals I naught prime plus I naught double prime. That's 52 minus 60 over 17. So that's minus 8 over 17. Okay? Now, if you want my personal opinion, solving this circuit using superposition is a waste of time. Honestly. Because what did you end up doing? You ended up producing the first circuit, this one here, and doing a mesh current analysis, a mesh analysis with 3 meshes. And then doing another one here, another mesh analysis with 2 meshes, right? So could it have been possible to use the original circuit and just do a mesh analysis right from the start here? You know, just have 3 meshes, do it for once and you're done, right? Okay. So a problem like that is not the best example, not the best problem to apply superposition to. So superposition, as I said, is good when you don't have dependent sources, and when you're applying it, your circuit really kind of gets reduced to something much easier to manage. That's fun. But if you have a large circuit with lots of sources and dependent sources, then sometimes using superposition is not the best choice. But again, superposition is very important because it's the basis for doing or developing computer methods for solving. So that's why it's an important method. Okay, so this is the same thing, but see, this one does not have dependent sources. It should be a little bit better. Okay, let's see that. Okay, so first step, keep a 12-volt source acting alone. So my 3 amp is going to become an open circuit, and my 24 volts is going to become a short circuit. And you're going to have a circuit that looks like that. Okay, this is an open circuit here. And we're looking for this current, so I'm going to call this one here I prime. Is there anything we can do here to reduce this one a little bit? Can I simplify this circuit a bit? Any resistors in series or in parallel that you see? Well, look at that. Because this is an open circuit now, nothing exists here. So you have, look at these. Can you see what they are? What's that? They're in series, right? That's 8 plus 4, 12 ohm. And your circuit now is going to look like this. 12 ohm here, 4 ohm here. My 3 ohm is there, and my source is there. What else do you have? Can I simplify it further? Any other resistors that I can take together?
4 ohm and 4 ohm.
These here, they're in parallel, so I have 12 parallel with 4, right? So that's 12 times 4 over 12 plus 4. That's 3 ohm. Okay, nice. What do you have now? You have a current here, I prime. In fact, now these two are in series, so you get a total resistance here of 6 ohm. And the current I prime is equal to 12 over 6. That's 2 amps. Okay. So now I have I prime. I'm going to do the second part, second phase. Keep 24 volt source acting alone. And the circuit is going to look like this now. Okay. 3, 4 ohm. This now here is a short circuit, and here you have an open circuit, like that. This is an open circuit here, where the current source was. This is a short circuit where the voltage source was. Okay, again, how can I simplify this? 8 and 4 are still in series, right? So that's 12 ohm. Be careful here, that's the current we're trying to find. I double prime is here. Okay? Now, can you find the relation between the 4 and the 3 ohm? Are they in what kind of combination? 4 and 3. This one and this one. They're definitely not in series. In series is like wagons of a train. Okay, nothing comes in between them. But if you look at this node and this node, you have the 4 connected between those two nodes, and the 3 is also connected between the same two nodes. These are in parallel, okay? So if you take these together like that, you have 4 parallel with 3. That's 12 over 7 ohm. And now I'm getting a circuit that looks like that. Okay, but in this circuit, I don't see I naught double prime. Okay, that branch has vanished. So I'm going to solve here to get this current. Call it Ix. You can call it anything, it's just a variable. Okay, now Ix equals, actually, sorry, not that. I'm going to put it like this because of the plus and minus that I have here. Ix is 24 divided by 12 plus 12 over 7. Sorry? Oh yeah, sorry. Okay, just doing some math here. So I have 2, 2 and 8, 4. So that's 7 over 4 amps. Okay, that's this current Ix here. Ix, I'm going to bring it back to here. This is Ix. Okay, or this one. Now I need to find I naught double dash or double prime. This current Ix from here at this node is going to go through two parallel resistors, this one and this one. I naught double prime is the same as this current but with a negative sign. So I'm going to say I naught double prime. I'm going to put my negative sign and then I'm going to use current division. Ix times 4 over 3 plus 4 minus 4Ix over 7. That's what my I naught double prime is. And I have Ix minus 4 times Ix, which is 7 over 4 divided by 7. So that gives you minus 1. Okay, this is I naught double prime. Okay, after that, we still have to do third part. Keep the 3 amp source acting alone. So I'm just going to show you how the circuit is going to look like. I have here a short circuit, another short circuit up here, and that's how your circuit is going to look like. And this would be I naught triple prime. Okay? If you solve that, look in the textbook, they're going to give you I naught triple prime equals 1 amp. So finally, using superposition, I naught equals I naught prime plus I naught double prime plus I naught triple prime. It's equal to 2 minus 1 plus 1 equals 2 amps. Okay? So there you go. This is the superposition principle. And as I mentioned earlier, sometimes it's fun to use it, and sometimes it's a lot of work. So you have to be smart, like kind of look at your circuit and determine if this is the appropriate method that you should use. If you're thinking in terms of a test or a quiz or an exam, if I want you to use a particular method to solve a problem, I'm going to say so. I'm going to say, solve this problem using superposition, because I'm going to be testing you on on your understanding of the superposition method. If I'm not saying anything, I'm just giving you a circuit and say find, I naught in this circuit, then it would at that point be up to you to think what is the best method to use to find that current. Thank you very much. Thanks for the book.